So the normalized LMS algorithm could be approximated, and we found that it almost did not affect the adaptation rate. We can do similar approximations with the regular LMS algorithm, and there are a family of algorithms called the SignLMS algorithms. And we have three of them in particular: the sign error, the sign data, and the sign. So these are all of the same family and very similar. First, with the sign error, we're just going to replace the error with its sign. So that's going to look like this. Note that right now this is a real filter. If you have a complex filter, then you'll perform the sign operation on each of the real part and the imaginary part. And if mu is a power of 2, then this becomes a simple shift and add or subtract, which makes it very computationally efficient. Okay, the next one is the sign data. And you can probably figure out where this is going based on what the sign error did. In this case, when we're doing our weight update, we're just going to replace the x vector with a vector of the sign values. This is pretty self-explanatory. We will discuss some of these things together in just a moment, but first we'll introduce the sign algorithm. The sign algorithm is like the sign error and the sign data combined, in that instead of doing the sign of one and the actual value of the other, we do the sign of each of them. So these are the three basic SignLMS algorithms. A few comments about these. First, as you might expect, the sign algorithm isn't going to work as well as we might expect. The beauty of the sign algorithm is the weight update is simply an addition or subtraction of mu to the weight. The disadvantage is, since we're using the sign of the error and the sign of x, small errors will still result in the same size update as a large error would, which is inefficient. And we can't really take into account the contribution of x to the total error, because we're just looking at its sign, not its magnitude. So as a result, we have to pick a really small mu to make this work. So why would you ever use the sign algorithm? Well, it used to be a much bigger deal before hardware multipliers were common in processors. For example, the early processors I used in my first job in dealing with microcontrollers and computers didn't have a multiplier at all, and so something like this would be really useful for cutting in half the number of multiplies you'd need to use to implement an adaptive filter. The efficiency has made it part of the CCITT standard for ADPCM transmission. More recent methods of encoding speech and audio require enormously higher amounts of computation than the sign algorithm. But we can now do that. In the day, that was a little bit tricky. I don't see it used as often anymore, except where efficiency is very paramount, and it's okay if you have a slow adaptation speed. Next, let's talk about the sign data algorithm. The sign data algorithm works fairly well. If the regular LMS works okay, then so will the sign data in general. It degrades a bit if the statistics of x of n change. And those are the cases where we would really like to have the approximate LMS algorithm, or NLMS algorithm rather. But for regular LMS, the sign data is a reasonable approximation that reduces the amount of computation required. One thing to note with the sign data is that, like the sign, your update requires only an addition or a subtraction. What's different is that rather than adding or subtracting mu, we add or subtract the quantity mu times e. The last is the sign error algorithm. The sign error algorithm is not nearly as good as the sign data, and the reason why is the step size doesn't decrease as we get close to a solution. So if we want to have a reasonable misadjustment error, we need to have a very small mu. The sign data does not have that same limitation.